Now let us see the applications of Kohlrausch law. The first application is to find the molar conductance at infinite dilution or the limiting molar conductivity of weak electrolytes. Yes, we can find out the limiting molar conductivity of weak electrolytes, but remember, this will be a theoretical value because we know graphically and experimentally that we cannot find out lambda naught for the weak electrolytes, but yes, theoretically we can find out. How? By manipulation method. Like, let us see, we wanted to know the limiting molar conductivity of ammonium hydroxide, which is a weak base. How can we find out? For this, we will select strong electrolytes with common ions. Like, we will select ammonium chloride. Now this salt, from this salt we can get the limiting molar conductivity of ammonium ions, and we can take NaOH. From here we will get the limiting molar conductivity of OH minus ions, and if we add the molar conductivities of at infinite dilution of the two, we will have sodium and chloride ions extra. So what we can do is we can take sodium chloride also, and what we can do is we can add these two and we will subtract the NaCl. Like, let us see here, the limiting molar conductivity of ammonium hydroxide can be written as the sum of limiting molar conductivity of ammonium chloride, NaOH, minus limiting molar conductivity of sodium chloride. Let's open them. What you get is limiting molar conductivity of ammonium ions, limiting molar conductivity of chloride ions, limiting molar conductivity of sodium ions, limiting molar conductivity of hydroxyl ions, minus limiting molar conductivity of sodium ions, minus limiting molar conductivity of chloride ions. Now these gets cancelled, so what we are left with only ammonium and hydroxide. So it gives and it solves our purpose because this is what is the Kohlrausch law of independent migration of ions is, that if, since we know that they will not dissociate completely, we cannot find out their lambda naught values, but yes, from the data of the strong electrolytes we can know the values of the lambda naughts of ammonium ions and the hydroxide ion. The moment we add them like this, we can get the lambda naught of ammonium hydroxide, which will be, of course, will be the theoretical value, that if suppose it dissociates completely, this would have been its maximum value. So this is how we can find out lambda naught or limiting molar conductivity for weak electrolytes. The second application of the Kohlrausch law is to find out degree of dissociation of weak electrolyte, which we know is the alpha. See, alpha of weak electrolyte we can easily find out that as that it will be the ratio of the molar conductivity at any concentration upon molar conductivity at infinite dilution. See, this will be the experimental value at any particular concentration, and this will be the theoretical value which we will determine as I have explained you in the previous application. So this is till what extent it has dissociated, and this will actually is depending upon if it dissociates completely. So the extent of dissociation divided by the total dissociation will give us the idea that how much the weak electrolyte has actually dissociated. So alpha can easily be determined by this ratio. Then third application is to find equilibrium constant for weak electrolyte. We know the dissociation of weak electrolytes will have an equilibrium, and therefore they will be having an equilibrium constant also. Now from the 11th class we know this equilibrium constant will be C alpha square 1 minus alpha. This will be the value, and remember, we will use this formula always. Now, if alpha is less than equal to 2%, we can take up to 5%, then 1 minus alpha is taken as 1, and then we can take what? That K equilibrium is equal to C alpha square. Then only we can use this formula. Otherwise, we have to use 1 minus alpha in the denominator also. So, we can find out the equilibrium constant for the weak electrolytes also. Now, let us see a numerical how we can use the informations given, which are actually by the Kohlrausch law, can be used in finding out the lambda naught for the weak electrolytes. The code numerical is find simple molar conductivity and limiting molar conductivity alpha, that means degree of dissociation, and equilibrium constant for acetic acid, which is a weak electrolyte. 0.1 molar solution of which shows resistance of 200 ohms in a cell of cell constant 2 per centimeter. What is given to us is given molar conductivity at infinite dilution, the limiting molar conductivity of potassium acetate, hydrogen bromide, and of KBr are this and this and this respectively. So, we have to first find out the simple limiting molar the molar conductivity at the concentration of 0.1 molar. So, we know the formula that the molar conductivity is 1 by R into cell constant into 1000 upon the molarity. Now, we know that the resistance shown to by the solution is 200 ohms, the cell constant is 2, and the molarity is 0.1. Let us put all these values here. So, it will be 1 by 200 into 2 into 1000 by 0.1. So, it will be 100 and it will be 10. So, it is again is 100. So, it is 100 centimeter square ohms inverse per mole inverse. This is what is the lambda we have, molar conductivity have at concentration of 0.1 molar. Now, let us find out limiting molar conductivity of acetic acid. This can be determined by what? Taking these three strong electrolytes. We can add potassium acetate and HBr. From here we will get acetate ion. From here we will get H plus ions. The KBr is extra, so we will subtract KBr from the data. We will get the lambda naught for this. The limiting molar conductivity of acetic acid will be the sum of potassium acetate HBr minus KBr. So, it will be 1100 plus 1300 minus 1200. So, it will be actually 1200 centimeter square ohms inverse per mole. So, this is what is R is lambda naught, limiting molar conductivity. Now, once we know the limiting molar conductivity, we can find out the alpha degree of dissociation, which is the ratio of the molar conductivity at any concentration, which was given to us as 0.1 molar, and divided by the limiting molar conductivity. So, this was 100 and this is 1200. So, this is 1 by 12. So, this is 1 by 12, we can take it as 0.083 as the alpha, or it will be, we can say 8.3%. Now, we know the equilibrium constant, which will be C alpha square 1 minus alpha. Since alpha is 8.3%, it is large enough, we cannot neglect this from the denominator. It will be your concentration, we were knowing it was 0.1 molar. So, it will be 0.08, we can take 8 3 into 0.083 upon 1 minus 0.083. So it will come out to be your 0.1, or we can write it as 8.3 into 8.3 into 10 to the power minus 5. You can write it here. So your equilibrium will be 8.3 into 8.3 into 10 to the power minus 5 upon, it will be your 0.917. So this 8.3 into 8.3 into 10 to the power minus 5 upon 0.917 on division gives us 7.5. It is actually, it will come out to be 75.2. So we can take it as 7.52 into 10 to the power minus 4. So this is what is the value of the equilibrium constant is. So this is how we can find out all these essential values from the given data as per the Kohlrausch law.